Hey, welcome to our very last lab, and it will be the crystal lab, in which we're going to be determining some things about sodium potassium tartrate crystal. Now, the first thing, and it's very simple in terms of the procedure, you do need to weigh out 35 grams of the potassium sodium tartrate. And in terms of that, what you want to make sure that you do, oops, my little doodad is loveliness, is that it is around 35 grams. And please make sure that somewhere you're writing down the exact amount. We don't want to go too much above or below this number because we're trying to obtain a super saturated solution, and we've determined that this is a very good amount. Then add about 28 mils of deionized water, and again, keep very close to this amount. It doesn't have to be exactly 28.00, but we don't really want to go like a milliliter above or below, simply because we are trying to supersaturate the solution. Now, the main thing is that you're going to be doing in lab is just basically dissolving this solid. Now, the asterisk sign here is just like in class with a dot. In that this is a hydrated complex. There are 4 water molecules essentially internally bound to this potassium sodium tartrate. And so it is included as the entire molecule. Now, essentially what you'll do is make your own water bath using hot tap water, and that's all we need to have in here. So we'll have some hot tap water and fill it about halfway, 2/3 full with hot tap water, and place your 100 ml flask then, 100 ml beaker, sorry, that holds your deionized water and your sodium potassium tartrate, and put that into the water bath. Essentially, you'll use a stir rod, and you will just stir this until all of the solid dissolves. Now, if the water cools down, make sure that you remove your small beaker and add more hot tap water to your bath, and then continue stirring with your small beaker. Excuse me. And so one of the things that you want to make sure of, and we used a hot water bath for our lovely back titration lab, you just want to make sure that no water is actually spilling into the smaller beaker. Because we again want to be very particular about the amount of solvent here that we're using inside the small beaker. Now, once your complete amount of solid is dissolved, and so this may take a while, then you're going to be taking that and pouring then this solution that you have made, okay, and you will pour that into a new clean beaker, and it doesn't matter what size beaker that is. And you will pour that solution then into the beaker. Now you want to add 1, yes, I said 1. Did I say 1? Oh yeah, I said 1 seed crystal. And so you'll go over to the beaker that has the seed crystals in it, and using tweezers, only choose 1. And put that 1 hopefully into the middle of this beaker here. And this will allow a nucleation site. And so this seed crystal essentially is a place for your crystal of the potassium sodium tartrate to start growing. And so from the solution, what will happen is each of these molecules can grab onto the nucleation crystal here, the seed crystal, and this crystal can start growing and growing and growing over the upcoming week. And so what we are trying to do is, of course, get a crystal that will grow out, that will be of substantial size, around 2 centimeters in length. Now, what you will need to do is you will need to, of course, then label this particular beaker with the name of the chemical and your full name, first and last, Chem 162, and your lab date and time, okay? And then this is going to be stored into the bin in front of the room. Now, in order to minimize the amount of contamination or multiple nucleation sites within the beaker, you need to make sure that you put some press and seal plastic over the top of the beaker so that dust cannot filter in from the room and cause multiple nucleation sites within your solution. Because the more nucleation sites you have, the smaller the crystals you'll grow. You'll make a whole bunch of little crystals versus one big crystal. And have you do a cleaning job. Now, in the next week then, so a week from Wednesday, we are going to come into lab and you will get your beakers back and you will select a crystal from your beaker. Now, a couple of things can happen with the crystal growth. Sometimes people get one large crystal. It'll be really easy to deal with this then. And sometimes the crystal, though, is growing on the side of another one. And we want to really look at just one crystal. And so if we remove this crystal from the supernatant, and the supernatant is just the liquid that is above the crystal, you can actually stick your fingers in there, not a biggie. And if you just press on the crystal near where it is connected to the second crystal, it will snap away and you will get one crystal to look at. Now, this is, of course, a great scenario. Some of you, though, may come in and you have hundreds upon hundreds of small crystals. And this may be due to your beaker not being very clean. And so if your beaker was not spotlessly clean, there are multiple nucleation sites for the crystals to grow. And it's much, much harder then to get a volume of a crystal. And so if anybody else in the room has an extra large crystal, you might want to borrow it from them. Otherwise, you will have to take one of your small crystals and try to determine its volume. Now, the first thing you should do when you take your crystal out of the supernatant, save your supernatant. Do not be putting this down the drain. Absolutely save it. So just pick out your crystals. Okay? Use your fingers, use tweezers, whatever, but fingers are fine. The first thing you're going to want to do is draw a picture of your crystal onto the data sheet, the data report sheet. And so again, you don't need to be an artist, but maybe if it's a trapezoid, you want to say, all right, we got this three-dimensional trapezoid here, and, you know, it has a little bit of an inclusion or whatever. But you want to, you know, basically draw what your crystal looks like. Then the next thing you're going to do is find out how many grams does your crystal weigh. Because what we are going to be looking at is the number of atoms of the potassium sodium tartrate there are in one unit cell. Okay, and so we have done problems like this in class where we can relate the density, which is just the mass of the object over the volume of the object. We can relate that to things like number of atoms. Okay, and so that's what we're going to do. So we need to find the density of this crystal. So we'll weigh it, and then we need to determine the volume, and that will be in milliliters, or you can think about that as centimeters cubed if you would like. By displacement. So what you will do is you will pour out of your beaker that supernatant into a graduated cylinder. Now, because our crystals are fairly big size, we may either have to use the 50 ml graduated cylinder that is out on the counter or a 100 ml graduated cylinder. There's using that graduated cylinder. And remember to record it to the correct number of significant digits for that graduated cylinder. Now, then you will take your crystal and carefully put it into your graduated cylinder. We don't really want it to splash up any of the supernatant onto the sides of the graduated cylinder. And then, of course, then the supernatant level will rise due to the volume exerted by the crystal. So here's our crystal down here, and we have displaced a volume. And so we're going to, of course, record that final volume in milliliters. And then, of course, the difference is the volume of our crystal in milliliters. Record that on your report sheet. Then, of course, you can find density. Density, of course, is the mass divided by the volume. Now, you will be graded on the accuracy of this density because I happen to know what the density is, okay? And so we're going to be looking at that from your data. Now, it's not going to be a lot of points, though, so don't be like freaking out. Now, what you will do then is you can use this density and the molar mass of the potassium sodium tartrate and the volume of a unit cell. Now, the volume of your unit cell, you have already basically determined on the Prelab, because on the Prelab, you were given these 3 units here. The cell side lengths Okay, and this is not a cubic unit cell because you'll notice A does not equal B, does not equal C. Okay, and so these are in angstroms. Okay, and we know that 10 to the minus 8th centimeters is 1 angstrom. Okay, and so you want to find the volume of your unit cell, because if you have that in centimeters cubed, if you were to multiply that by the density, the centimeters cubed would cancel and you would now have grams. Can you go from grams into number of atoms? Whoops. Sorry about that. Now, this centimeters cubed, this is the volume of 1 unit cell. So you can get the number of atoms in 1 unit cell, okay, using your density. Now, I want you to record the number of molecules to the nearest tenth. So you might say that there is 2.1 atoms per unit cell, okay? Don't round off to a whole number, okay? Now, I will tell you that the number of atoms is going to be less than 100, okay? Because we don't have a cubic unit cell, it's not going to be something like 8 or 4 or 1 or 2 or anything like that, okay? It is going to be some number less than 100. If it's more than 100, you have done something wrong. Now, here is your data and report sheet. This sheet, of course, is going to be the first sheet that you hand in, along with some others. But you'll notice here we'll have day and time. This is an individual lab. And so you're going to staple this sheet in the front. And then there are 2 pages of post-lab questions that are posted in Canvas for you to answer. And then it asks here, actually in the Canvas page, to put your calculations on the back of this sheet. I don't want that. I want my calculation sheet on a separate page. The best bet for you is, of course, to put that calculation in your lab notebook, so you can use it for that week's post-lab quiz. Now, you'll see here we have places for all of your data and your results. So you're going to be drawing your sketch of your crystal. You're going to describe its shape. Does it look like a cube? Is it oval? Is it look like a trapezoid? Is it triangular? And that's all we're going for there. So your number of unit cells is going to go to the 10th, okay? And of course, this is, of course, how many molecules. Sorry, not atoms. So if we go back here, this is molecules. I apologize for that. Now, it says, to what crystal system does this belong? And so what you'll be looking at is your A, B, and C values. They're not all equal. And then you're looking at your alpha, your beta, and your gamma, your actual angles on this thing, and looking at the number of the unit cells found in your procedure and your background for this lab, you'll be able to determine which unit cell you have. Now, the other thing that is on this report sheet is a problem, and it's dealing with the tartrate dianion. It has 2 negative charges here, 1 on each end. And this is trying to show you what atoms are bonded to what other atoms. So here, this first carbon says it is bonded to 2 O's. And then it says this carbon is bonded to this thing written out twice. So this C has got an H on it, and it has an OH. And it says to draw this 2 times. Now, what we'll know in structures like this with most organic compounds is that the carbon needs to be bonded 4 times. And so over here, you're going to have to think about what to do to make sure that this is bonded 4 times. And then, of course, don't forget the charges. There's a -2 charge on this molecule as a whole, a minus on each end. So the first part says draw the skeleton. So again, essentially, it's just the stick structure. And then it asks to do the Lewis dot picture of this. So making sure that you have lone pairs on whoever needs lone pairs. You'll have to add up how many electrons are going to be in the picture and include all the dots and the charges for this picture. Now, the post-lab questions, of course, are posted on Canvas. There are 2 pages